In this video, I want to have a look at the nature of our stationary points. So we've already had a look at how we can determine where our stationary points are, but we want to have a look at the different types of stationary points as well. So the first type of stationary point we can have is a minimum turning point. So we have a stationary point just here because the gradient of the tangent at that point is 0. And we can see that at that point, it changes from being a negative or decreasing function to being an increasing function. So it's changing from a negative gradient to a positive gradient on either side of that stationary point. So as you can probably guess, the next type of stationary point is a maximum turning point. So we have our stationary point here, where the gradient of the tangent is 0. But this time we're going from it being an increasing function, so a positive gradient, to being a decreasing function. So it's got that negative gradient there, and it's changing at that stationary point. The last type of stationary point we have is what's called a horizontal point of inflection. So we've got two versions here. We've got an increasing and a decreasing horizontal point of inflection. So we'll just write that on them. So this one's increasing. And the reason it's increasing is because our stationary point is right here in the middle. Now on the left-hand side of that, this section of our function is an increasing function. It's got a positive gradient. And over here, it's increasing as well. So it hasn't changed like our turning points did. It hasn't changed from one to the other. On both sides, it's increasing. But at that stationary point, of course, the gradient of the tangent at that point is 0. So I've got the same thing over here. So on this left-hand side, that's a decreasing function there. And on the right-hand side of that stationary point, it's a decreasing function as well. So this one here is a decreasing point, horizontal point of inflection. So the curve is either increasing on both sides of the stationary point or decreasing on both sides. So it's not a turning point. Instead, it's actually changing concavity around those points. So here, this section of the curve is concave down, and this section here is concave up. Whereas in this one, this section is concave up, and this section here is concave down. So we have 4 different types of stationary points. Now we can determine the nature of stationary points of a function if we've got a graph just from looking at it. But often we won't be given the graph, we'll be given the function itself. So for example, we've got the function f of x equals 3x to the power of 4 minus 8x cubed. And we're asked to determine the nature of the stationary points and then graph that function. So we're going to go through first and figure out where the stationary points are, and then we'll have a look at how we can determine their nature without graphing it. So our first part, if we want to find where those stationary points are, we're going to have to find where the first derivative is equal to 0. So we want the gradient of the tangent to be equal to 0. So we have our function up here, so let's find that first derivative. So we're going to differentiate that function. So 4 times 3 would give us 12x cubed, and 8 times 3 is 24, so we'd have minus 24x squared. Now we want that to be equal to 0, so we'll have 12x cubed minus 24x squared equals 0. So to solve that, we can factorise by pulling out common factors. So we'll pull out a 12x squared, and we'll be left with x minus 2 equals 0, which is going to mean that either x is equal to 0, or that whole x minus 2 is equal to 0, which would mean that x equals 2. So we've now found the x values where the stationary points exist, but because we want to find the coordinates of the stationary points, we also need to find the y values. To do that, we're going to substitute these values back into the original function. So we're going to find f of 0, which means we're going to substitute 0 in here. So we would have 3 times 0 to the power of 4 minus 8 times 0 cubed, which will just be 0. And I'm going to move this one over a little bit. And f of 2 would be 3 times 2 to the power of 4 minus 8 times 2 cubed, which will give us minus 16. So that means we have 2 stationary points. One of them is at 0, 0, and one of them is at 2 minus 16. So that's part A. Part B, we're needing to find or determine the nature of these stationary points. So we need to figure out whether there's at these points, whether it's a minimum, a maximum, or a point of inflection. The way we're going to do that is to test whether it's an increasing or decreasing function on either side of those points. So we're going to draw up a table of values. We're going to have our x values, and we're going to have the value of our derivative at those points, at the x values. So the values we need in here, we need our stationary points. So we know they're at x equals 0 and x equals 2. But we also need to test points on either side of those. So in between 0 and 2, may as well pick 1, 3, and -1. What those values are doesn't matter as long as they're between your stationary points or on either side of your stationary points. So we know that the value of the derivative at 0, so if we substituted 0 in here, we would get 0. Same with this 2, because that's how we found those points originally. So we know that the gradient of the tangent at those points is horizontal. So we'll draw a little horizontal line underneath them. Now we need to find whether the gradient of the the gradient of the tangent at these other points is positive or negative to figure out whether it's increasing or decreasing. So if we find f dash of -1, so that means we're going to substitute -1 into this equation here. So we'd have 12 times -1 cubed minus 24 times -1 squared. If you pop all of that in your calculator, you'll end up with -36. Now we don't actually care what that number is, we only care if it's positive or negative. So because it's negative, we're going to draw in a line with a negative gradient here. Now we need to do the same thing for f of 1. So we'll substitute, f dash of 1. So we'll substitute 1 into here for our x's. So we'll have 12 times 1 cubed minus 24 times 1 squared, which would give us -12. So again, that's negative, and I haven't really left myself enough room here, but that's negative there. So we're drawing it off our horizontal line, and we can see from that little diagram that that's going to be a point of inflection. If it's got a decreasing function, and then it's 0, and then it's decreasing, so it's decreasing on both sides of our point of inflection, of our stationary point, means it's going to be a point of inflection. It also means that that point is to the left of our second stationary point, so it's decreasing over here as well. All right, now last one, f dash 3. So we'll substitute 3 in there, so we'll have 12 times 3 cubed minus 24 times 3 squared, which will give us 243. So 243 is a positive number, so that means that our gradient is positive, so the function is increasing over there. What that means is 0, 0 is a decreasing point of inflection, and that the point 2 minus 16 is a minimum point, so it's going from decreasing to increasing. All right, so that's parts A and B. We found where the stationary points are and we found their nature. Part C asks us to sketch a graph of the function. This isn't straight at all, I'm sorry, but you're going to use a ruler on yours. We do have the points 0, 0, and we have the point 2 minus 16. So we know that there is a point of inflection, a stationary point here and here. We know that this one is a decreasing point of inflection, so it's going to look like this. And we know that this one is a minimum. So we're going to join those together to sketch our graph. So that one's going to come up here. This one's going to curve down and around. And this one's going to come up this direction. So that is our function f of x.